So what we're going to talk about today, the things I want to talk about, are sort of more about actual combustion chemistry. So I spent a lot of time talking about how you compute rate coefficients in general, how you build kinetic models in general, but I didn't actually talk about it, real fuels and real reactions and stuff. So I'm going to talk about that. And I'm going to focus on two big problems in the combustion chemistry that are of great interest recently to people, and try to at least have you understand well enough what the issues are and what that's about. So you'll know you'll probably read a lot of papers about these topics in the next few years, and so you know what people are worried about. So first I'll just go through and talk about some three kind of typical issues we have. So one issue is we have diffusion flames. And actually many real combustors and real devices work that way. And as you'll see, it's very advantageous from the point of view of the mechanical engineers because the mixing really controls the rate. So you can just change the mixing by the way you run the flows, and you can control the rate. Whereas in the premix flames, the rate of the reaction, the rate of the heat releases really depends on the fuel and the chemistry, at least to some extent. So you have less control over exactly what's going to happen. And then finally, we'll get into ignition, particularly low temperature ignition, where it's almost completely controlled by the fuel, and the only variable that you have as mechanical engineers to control is really the temperature. And so if you change the fuel, you'll have some wildly different behavior because it's very chemistry sensitive. The diffusion flames, a very major problem with them is that they make soot. And that's a major health problem and also a practical problem in operating the engines. And so I'll talk a bit about that. And there's a bunch of things about soot that we really don't understand or only starting to understand. So I'll try to explain about that. And I need to acknowledge Hai Wang, whose slides I'm going to show you from a talk he gave in 2010 at the Combustion Symposium. And then some figures that my student Shamel Merchant made recently. They're in a manuscript that we're revising right now. All right. So a common kind of combustion geometry is you'll have a fuel injector and it's squirting out fuel. And maybe this is entraining some air, possibly. And somewhere over here is a flame. And over here is air. And so you have a flame where on one side of the flame it's basically fuel, possibly a little bit of air. On the other side is basically air. So this is a very common configuration. So this is the way diesel engines work, and many burners work this way. It's very safe because you keep the fuel and the air separated until you want them to burn. So that's really important from a safety point of view. And it's also easy to control, as we'll see in a minute, because the rate of this reaction is basically how fast you can get the fuel and the air to that interface where they meet each other. And that's all about the flows. And so if you can control the flows, you can control that. And the chemistry doesn't really matter because once you have a flame established, the temperature's so hot here that basically everything that gets there is going to burn up. So it's just, you're just rate limited by how fast you can get the material there. And so this is this approximation that once you have the flame going, you don't need to worry about chemistry anymore. Often is expressed this way. So you might have heard this before. And so for a long time, combustion device simulations, they always made this approximation. And they called, if you tried to do anything else, they called, you were doing something strange. And they would call that finite rate chemistry. And they were like, oh, well, why would you ever assume that chemistry had a finite rate? This is a very strange thing to assume. So if you assume the chemistry is infinite rate, then this is what you get. As soon as it's mixed, it's burnt. Right away to equilibrium. Okay? But this is actually very realistic for a lot of real devices. So that that modeling paradigm worked very well. And I mean, the jet engines that we drive today and the diesel engines we drive today mostly were designed by people who just made that approximation, mixed as burnt. And actually, the whole interest in finite rate chemistry and not making that approximation got to happen when people started worrying about emissions. Because in emissions, obviously, you change something and you get different amount of like formaldehyde or benzene or something being made, or NO. And so obviously there's something that's more than just how much is mixed. And so then people got into worrying about the chemistry. But for a long time, you can handle this kind of configuration without it. Now, the way this is written, it looks kind of complicated. And so a simpler way people look at this is I have my flame. Over here I have my air. Here I have my fuel. And I just considered that the fuel is diffusing. And then a common configuration like this is like a simple jet burner. You have a fuel, you have air over here, fuel here. And the fuel is moving this way, but the important motion is perpendicular to that. It's the diffusion of the fuel and the air to come together. And in fact, the length of these flames is almost exactly predicted by the diffusivity and the diameter. So you just take those two numbers and figure out what the length would be. And the velocity is telling you how fast it's going to give you the time scale. So if you take the diffusivity, the diameter, or the radius, I guess, maybe, radius, and the velocity, and you put them together into the group that has the right dimension of length, that'll tell you the length of the flame. So it's just how long it takes the air to diffuse to the center. And in this kind of configuration, the temperature is really spiked right in the flame zone, and it'll be maybe something close to the adiabatic flame temperature. So you have a very high temperature zone, and to first approximation, all the reactions are super fast. Because in that zone, you have very high temperature, and you have a lot of radicals, because of the H plus O2 reaction is running like crazy, making bushels of radicals. And so basically, you can catalyze any reaction with all those radicals, and you basically everything just goes to whatever equilibrium you can do, which is mostly CO2 and water vapor. And so that's what you got in there. The problematic aspect of this is that you have such a high temperature there, you're going to have a lot of NO be formed, because you have a lot of O atoms formed. So you have your main reaction is H plus O2 goes to OH plus O. The O atoms, you have a lot of nitrogen in there because it's in the air. So this reaction runs. And even though this is very endothermic, because N atoms are very energetic, the temperature is so high in there that you can actually make this run. And once you make an N atom, they react with oxygen very fast. And then you have a chain reaction running, and you're constantly feeding more O atoms into it from your main reaction. So this makes a lot of NOx. And so that's why we have problems with diesel engines, for example, making NO, because just the way they set it up, you're going to make a lot of NO. Now, if we want to model this chemistry-wise, we do want to consider finite rate chemistry. On the air side, there's not much to model. What do you have over here? You have O2, you have N2, and then maybe you have a little bit of H atoms or OH or O atoms that are diffusing out of the flame. You have some temperature, but there's nothing to burn over here. So basically nothing's going to happen. So the air side is boring, not so interesting to model. Its temperature drops off pretty fast as you get away from the flame front. And so this reaction drops off because this is very, very endothermic, so that it has very sensitive to temperature. So basically the air side's not interesting chemically. But the fuel side's really interesting because we start with some big giant molecule, something like this. Suppose we have a butane flame. We start a big butane molecule, and somehow this thing is going to rip apart and break down as it gets closer and closer. Now, for sure, if it makes it all the way to the zone, it's going to get burned up by reacting with the OH radicals. We'll attack it and make it burn up. But actually, it doesn't actually make it that far. So as it gets closer, the temperature field is like this. And once it gets into a zone where the temperature is high enough, it'll actually start just reacting by itself Just like if you take some vegetable oil and you cook it on your stove, even if you didn't have any oxygen there, you could still make it turn black and turn into some horrible thing. The same thing happens here. If you have fuel, you'll crack it. Just like in a candle, you have the wax, which is like an alkane, the paraffin wax. The paraffin wax melts, and then it evaporates, and it actually chemically cracks before it even gets into the flame because of the cracking reactions. And the main sequence is you have your fuel gets attacked by some radical, and oftentimes this radical might be H atoms. And it goes to the fuel radical, and then the fuel radical beta scissions, and it makes an alkene plus a smaller radical. And if this radical is still big enough, it'll do the same thing again and break off and give another alkene and smaller radical. And it keeps happening over and over again until the R dot is too small to beta scission. So until basically the R dot is equal to CH3 or H atoms, because these sides don't have any bond beta to the radical site that can break. So that'll stop. And this unzipping is pretty fast. So around 1,000 Kelvin, it has a time scale of seconds. By the time you get up to about 1,400 Kelvin, it's like time scales of milliseconds. And so as you get closer, as the fuel is diffusing closer and closer, it's feeling the heat. It lives long enough, typically, that the temperature's out far enough and takes long enough to get to the flame front that before it gets there, it's actually all gone. So there's no fuel actually entering the flame. What's entering the flame are these alkenes that you made. And then these guys that it ends up as, these will convert to methane and H2. So you have H2, methane, and alkenes. If the alkenes are big enough, they'll act just like fuel, and they'll also break. So the large alkenes also break, and they go down to small alkenes, plus some small R dot. And what you get here altogether is you end up with a lot of C2H4, that's the smallest alkene, ethene, and also propene, CH3. That's what most of what the mass ends up as. So you put mass in as fuel, and before it actually reaches the flame front, almost all that mass is now in the form of ethene and propene, and there's also a significant amount of hydrogen and CH4. Now this process is known very, very well because this is actually a commercial process when you run at 1,000 Kelvin. That's called steam cracking, and it's the biggest chemical process. So all the chemical companies of the world have studied this for forever, or at least since World War II or something, when they started making alkenes. And the alkenes are the monomers to make polyethylene, polypropylene, and all the other polymers. So like the cloth you're sitting on, the cushions inside, your clothing, your shoes, almost everything in this room is polymers that were made by this reaction. First they make the alkenes, and then they carefully control the polymerization to make them have the right size polymers that have the right toughness, flexibility, ductility. You can make them into fibers. You can make them into plastic bags. You can make them into hard plastic struts that we use to hold things up. Make them into the carpet. All these things are from that.
What controls the beta scission? You got the butane there. What controls if you're going to propane or say to methyl?
Yeah, so it depends which H gets pulled off first. So if first I pull the first one off, I'll start with this, CH2, 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 CH3. And this will break to CH2, CH2, that's ethylene, plus CH2, CH3. So that's if I break this bond, beta to the radical. And then this guy will spit out an H, and it'll go to another C2H4 plus an H atom. But if the initial radical, the first OH, came up and hit the other hydrogen first, it would start this way. And this would break to CH3, CH2, propene, plus methyl. So it's which one they hit. And exactly the selectivity of whether they want to grab one H or the other, they're slightly different rates. And it depends if it's an H atom attacking or a CH3 attacking. And so it's a slightly complicated calculation to figure out what ratio of ethylene to propylene you're going to make. And so, but this is a very important calculation because petrochemical industries cares about this deeply. Because if you're running one of these plants, you get paid different amounts for propylene than you do for ethylene, and you don't get paid nothing for methane. You really carefully try to understand this, and this is very well understood for a lot of fuels and exactly what temperature and pressure you should run at in order to make it favorable to get a break one way or the other way. And actually, I just met a guy last week. I was in Belgium at a place where they have a steam cracker, and he was saying that if you could change the ratio of propylene to ethylene by 0.1%, for the one unit he had, it was worth $5 million a year. So they really care. But that's all around 1100 Kelvin. In the flames, more typically, it's breaking down about 1400 Kelvin because we don't have a whole second for the fuel to get into the flame. It takes milliseconds instead. But that just means that most of the chemistry is happening around 1400 Kelvin, and then the adiabatic flame temperature is like 2000 or something. So you're sort of halfway up this temperature ramp when the stuff breaks. All right. So we have all this pyrolysis chemistry happening on the side, and you get some of the radicals in there are from the H atoms from the combustion are diffusing. So there's H radicals created in the flame and actually OH radicals and O radicals. There's radicals created in the flame, and they're diffusing in both directions. And some of them are diffusing into the fuel, and so they're helping to drive this chemistry. But actually, most importantly is the temperature, because this chemistry, it's a chain reaction. So I have one radical in, I get one radical out. This H is then going to go back and attack another butane molecule. And the same thing with the CH3. So once you get this going, it's sort of self-sustaining, or every radical you get into the system might destroy 1,000 butane molecules. And then on top of that, if you make, there's sort of a side reaction that this, for example, could make CH2, CH2, CH3 plus H atoms. So that it can go either way. This is faster, but this is still significant. This is a double bond here, plus an H atom. This kind of thing actually has a weak bond here. So it can just break to two radicals. So at 1400, 1500 Kelvin, this might break pretty high probability. That creates even more radicals in the system. So you have ways of making more radicals in addition to the fact you have a flux of radicals coming in from the flame. So cumulatively, that poor butane molecule has no chance because there's a zillion radicals coming in. The temperature's so high that all the rates are super fast. Once you loses one hydrogen, the whole thing's going to unzip down into ethylene and propylene. And that's what happens to all your fuels. And so that's with butane, but it's not just butane. So almost all the fuels you can think of, this kind of thing happens to it. So pretty quickly, all the large molecules are gone, and you're left with a mixture primarily of small alkenes, primarily ethylene. It turns out to be the biggest one. Also hydrogen, also methane. And then actually, if your fuel had some aromatic rings in it, the aromatic rings can survive. So they'll still be there. So they'll lose all their side chains. And you'll have benzene and toluene, maybe xylene. All the other bigger alkyl aromatics would have lost all the alkyl chains. Maybe some styrene, a little bit. And so that's the main chemistry that's happening. Now this is the main chemistry if you're just fuel pyrolysis. So if you have a perfect diffusion flame, perfectly non-premixed, even if it's partially premixed, the same chemistry happens. At those high temperatures, these beta scission reactions are very, very fast. So these happen even faster than it can react with O2. So it's zip before it can react with O2. If you make an H atom, the H atom will react with the O2 and make more radicals if you had some O2 there. And what happens pretty quickly in that kind of environment is that all the O2, however much O2 you had in there, is consumed if you're fuel rich. So all the O2 will be consumed. You'll make some water, you'll make some CO, and then you've heated even hotter, and now you really blast the fuel. It's all gone. And you get basically, it's a very similar mix of products because the O2 doesn't really divert the chemistry very much. So basically it's determined primarily by this branching ratio about whether or not you made this radical or this radical, and then these kind of branching ratios about whether it goes to make this alkene or that alkene. Any questions about this? So one consequence of this is that if you, oh, sorry, question? Yeah.
So if the fuel doesn't make it to the high temperature regions,
Yeah.
why is it important to include unimolecular decomposition reactions?
In what?
I mean, like these require high temperatures, right? They are high energy barrier reactions.
Yeah.
And if the fuel doesn't make it to the high temperature regions, then these reactions should not be important, right?
Right. So a good question. So the question was, why do we need to include unimolecular decomposition reactions of the stable molecules? Is that the,
Of the fuel molecule.
of the fuel molecule? Yeah. Why would we ever want to include unimolecular decomposition reactions of the fuel molecules in our simulations? And I think my answer is a lot of times you don't have to. So the fuel itself, if it doesn't have any double bonds in it, its unimolecular decomposition is very slow. Even at 1400 Kelvin, it's pretty slow. And so it's most likely, if you have enough radicals around, it's going to live and be attacked by a radical and it's be destroyed by the radical. So in many, many situations, all the decomposition of the fuel is radical driven, and not the unimolecular by itself doesn't really matter. And it's sort of unusual special situations where there's something suppressing the radical chemistry, where the unimolecular decomposition can be important. Sometimes at very, very low pressures. So some low pressure flames that people use is like for scientific experiments, not practical flames, but really, really low pressure. Then you can have a case where the pressure is so low that all the bimolecular reactions are suppressed a lot. And so then the unimolecular reaction can compete. Yeah.
So you mentioned about it's a case for alkane, but it's not the case for benzene aromatics. But what about fuels with a lot of triple bond and double bond? Will be
yeah, so this kind of chemistry, if you start with ethylene, for example, you can still do this kind of chemistry and you'll make a lot of acetylene, C2H2. But at that point it stops because there's no easy thing to make next by unimolecular reactions of acetylene. So you'll just make bushels of acetylene. And that's actually what I was going to talk about next. I'll come back right back to that. If you start with benzene, I'm not really sure what happens, but I think you just have a lot of benzene that gets through up to the flame, because I think you need the oxygen from the flame to actually make the benzene burn up very well.
triple bond, so double bonds in non-chan fuels, this double bond will stay.
Double bond will stay, and you'll just cleave off all the part with single bonds. Yeah, and you'll end up with like a propene probably as your one fragment, and then you'll end up whatever happened. The other one will break. The long alkyl chain will break in just like this, and make a mix of propene and ethylene.
And triple bond the same.
Triple bonds will stay.
What about alcohols, like say with OH, and also you have the
Yeah, so alcohols. Alcohols. So the question is, how do alcohols pyrolyze? If you have say propanol, the CH that's easiest to attack is the one that's next to the OH. So that's preferentially attacked by most radicals. So you'll mostly make this as the first radical. So this is the primary radical. And then the main reaction that happens is in pyrolytic conditions with no oxygen. So this is with no oxygen. This will go to CH3. So this is CH3. So I'll write the hydrogen. H2, CH2. This will go to CH3 plus CH2, CH2OH. So that's the main initial decomposition for yeah, it makes enol. If you have oxygen present, the reaction of this thing with oxygen is super fast, and it'll primarily go to this. So this O2 adds to the radical, reaches back, grabs the H atom, and immediately falls off. And that whole thing is super fast. And there's a nice calculations done by Zador, and showing how it's just incredibly fast this is. So if you have any O2 around, this would happen. This bond is the weakest one. So this will next go to CH3, CH2, C, this thing. At high temperatures, the CO falls off instantly. And then this would spit out an H atom plus ethylene. So this really depends a lot if you have any O2 present, what the ratio is, the two ways. And then this thing, if you have a lot of H atoms present, this can catalyze it. I showed the reaction yesterday. And then this would go to CH3, CHO, sorry, C double bond, OH. And this would, again, this one would be attacked. It would go to CH3, CO dot. And this will mostly go to methyl radicals plus CO. So that's pure pyrolytic. You mostly end up with methyl and CO, plus another methyl from here. If it's longer chain alkane, this stuff over here, instead of being a methyl here, it would be some complicated R group. All right. And for every kind of fuel, you can track this down. They haven't all been tracked down yet. So people really spend a lot of time on alkanes and branched alkanes because that was the commercial interest to try to make the ethylene and propylene for the polymers. So that's really well studied.
You check down primarily based on beta CG and also what other?
So the main issue is you need an H subtraction to make a radical in the first place from your fuel, and then you just do the beta scission rules. And most things, that's all you need. And there's a few oddball ones like the alcohol with the O2 there. If you have some O2 present, you can sometimes get some odd reactions, but not much. Actually, at these temperatures, the beta scission, the radicals fall apart so quickly that usually they're gone before they can even react with an O2. And it really depends exactly what temperature. If you have O2 present, everything's a little bit faster. You make more radicals because some of the H's react with the O2 to make more radicals. So you get everything going at a lower temperature. So instead of having, if you had it partially premixed, so suppose you have a little bit plus a little bit of O2, like you might have in a real device, you wouldn't have pure fuel. You'd probably entrain a little bit of O2. Then all this chemistry, instead of happening at 1400 Kelvin, it might happen at 1200 Kelvin. And so you'd be a little bit further away from the fuel front when it starts to react because you have more radicals with the O2. The O2 reactions release a little bit of heat, so they raise it up. So the whole thing happens a little further distance from the flame front. And some of the reactions change a little bit. So you'll see, like, if you had alcohols, you'd see CO. In normal fuels, you'd see water vapor being made from the oxygen. All right. Now this whole discussion maybe raises the question of a topic called sealing temperature. This is a very important concept. So if you have a reaction that is some molecule breaking up into two molecules, then you always have to consider, well, it could go the other way around. It could go backwards. Oh. Does it still work? Yes. All right. So it could go backwards. So this really could be equilibrated. And you want to know what the equilibrium, does it favor going to the right or does it favor going backwards to the left? And we know it must be able to go backwards to the left because that's the commercial process of making all this great stuff we have around us by polymerization. All the polymers are made by adding the small molecules to the alkenes. And in fact, free radical polymerization is the way you make like plastic bags, polyethylene. So definitely this reaction can run backwards. And what it is that the delta H for this reaction is positive. This is an endothermic reaction. And the delta S is also positive because you're making two molecules out of one molecule. So that's a positive delta S. And because they're both positive, then the Kc definitely increases with temperature. And so the ratio, if you do the equilibrium ratio of these two radicals, it equals this thing. So I just took this equation and wrote it in terms of Kc. So Kc increases with temperature. And the temperature where the two concentrations of radicals are computed to be equal at equilibrium, that's called the sealing temperature. And sort of when you're above that temperature, the reaction wants to run to the right. If you are below that temperature, it runs to the left. So a polymer in general has a sealing temperature. You have any polymer and you put it in some heat. If you heat it hot enough, it'll turn back to the monomers. If you cool it and you have enough catalyst or reactivity for it to happen, the monomers will all go back and form the polymer again. Okay? So this is very important for us to understand the pyrolysis, to know where the sealing temperatures are, because the molecules are not going to start decomposing until they get to the place where they're near the sealing temperature. That's when you'll start getting significant decomposition. All right, so, and then the other point was what we talked about already, that the different fuels can make different mixtures of alkenes. And then what actually happens in the flame will depend on what the mixture is. And that's because ethene reacts with oxygen wildly different than all the other alkenes. So ethene reacts with oxygen very quickly to make carbon monoxide and formaldehyde, HCO, by that special reaction C2H3 plus O2. All the other alkenes do a different reaction. So for example, propene, well, I'll contrast them. So here's ethylene. What it does is it loses an H. The only H's it has, they're all the same. So if it loses any H by, say, abstraction by OH in a flame, you make this molecule. And this molecule has a magic well skipping reaction where it reacts with O2 and it makes formaldehyde plus HCO. And HCO at high temperatures immediately goes to H atoms plus CO. So this reaction is really great for burning because you absorb one radical, it makes an H atom radical, but H atoms, if I have oxygen present, are going to react with it O2 to make another OH radical and an O atom, which will make another OH radical. So this is like accelerating the process. This is exothermic like crazy because I made CO out of fuel. So I've made a lot more heat, so the temperature went up. I made more radicals too. And basically the whole thing's going to burn to smithereens. So this is great. This is if you're doing combustion, this is combustion. Okay? Contrast it with propene. So propene looks like this. Its only difference is it has one methyl group instead of one of the H's. But now when almost any radical comes up to this, what it's going to do is abstract this H, because this CH bond is very weak. Now why is that? That's because there's a resonance that the electron can be on either carbon sort of equally likely. And quantum mechanically, that turns out to stabilize the situation a lot. And that's because it's sort of like a Heisenberg uncertainty principle thing. That's sort of the delta X, where the electron can be, is now twice as big as it used to be, or even more. So it used to have to be over here. Now it can be like anywhere across this whole molecule. And as a consequence of that, the energy of it is much lower. It's much more stable. And so because the energy is lower, it's more stable. It doesn't want to react. It's like it's happy. It's already sort of near the bottom of a well or something. And so this stuff just sits around. And in particular, it will not react with O2. So if you want to make it react with O2, the sealing temperature for the reaction of this with O2 is way low temperature. You have to be like down at room temperature or even lower to make this react with O2. So it's not going to react with O2. It's just sitting there. It can still react by reacting with other radicals. So for example, if you had some HO2, that can react with it. If you had a CH3, it could add to it. But these are reactions with radicals, so it's two low concentration species together. And that's relatively unlikely. As opposed to this one, this is a reaction of the fuel molecule that's stable. This is a high concentration species. It's the main species coming out of my fuel into the flame. One radical, so it's a first order and small stuff. And then these are now, again, first order and small stuff. So everything here is first order and small concentration, so this is all fast. And in fact, this is barrierless. This is a teeny tiny barrier, so these are super fast. So once you get ethylene into a flame, it's burned up. But over here, you put propene into the flame, you get this first step right away. The propene goes to allyl radical. That's what this is called. But then this radical just sits there. And it has very slow second order reactions with the other radicals. And actually some of those reactions, it could react, for example, with H atoms, but it turns out if you compute the pressure dependence, it's way in the fall off region, so the rate coefficient's teeny tiny. So it basically has very little things it can do, so it's sitting there. And actually, what a lot of this stuff ends up being consumed by a kind of very slow reaction that's endothermic to go to this thing called allene, where it spits out this H atom. And so it's a beta scission, but it's a weird one because this H is on a C that has a double bond on it that makes this bond much stronger. So this is way endothermic. But it can go to there. If it gets to here, it'll easily be abstracted by another. So this one spits out an H. Or it could have another radical grab this H also. And then it reacts with another, say, OH, and it'll go to this species, propargyl. And this one really accumulates because it can't do nothing. Okay, so then you just have propargyl sitting around and it can't do anything. It has no more H's to lose, basically. It's down as far as it can go. You can't really draw any stable molecules after losing any more H's from here. It doesn't have any weak bond to break. The bond that would break beta scission would be a triple bond. It's definitely not going to break a triple bond. So it's stuck. So this stuff accumulates. And if you don't have enough oxygen present, this also will not burn because this is crucially depends on the O2 being there. So if you're in a region over on the left side here, and suppose I don't have any O2 on the left side, if I make those vinyl radicals, the C2H3s, they won't do this. This is if there's no O2 present, they'll just go to C2H2 plus H. This is acetylene. And so in the absence of O2, I'll accumulate acetylene and I'll accumulate propargyl radicals. And both of these guys are implicated in making lots of soot. So the propargyl radicals have formula C3H3. And if you add two of them together, that makes C6H6. What molecule is C6H6? Benzene. So that's super stable. So now this is like a quick way to make benzene. And if you have acetylene, it also has the same chemical formula as benzene. It's C2H2. You have to get three of them together, so the kinetics are poor. But once you start getting this happening, you can get to benzene. Now, benzene is also one of these resonant molecules, because the benzene has two ways you can draw it. And that makes it way unusually stable compared to all the other molecules. And so if you get to benzene, you're not going back. So benzene becomes like a sink to make benzene. And then if you're in a situation where you are still over here and you haven't made it to the flame front yet, and you've already gotten up to making benzene and you're having lots of acetylene, then you're likely to make lots and lots of soot. Because once you start, benzene turns out to be the rate limiting step forming the soot, typically. And so after that, you're in trouble. Now you look at the flame, like maybe a candle flame. So I have a nice little candle flame here. If I look at it, by the time I get up here, you can see little bits of black in your flame. You ever see this? In a candle flame, right? And then sometimes, in bad luck, they might even come through. And then you'll get the ceiling above the candle will get black stuff on it. Okay? So that's what happened, was that the heat from the fire, which is all along the sides here, it was heating this fuel all the time it was traveling up. And it got far enough along and there wasn't any oxygen around or not enough oxygen. And so you got all the way to acetylene and to propargyl radicals, and then you're going to make lots of soot.
So the soot essentially contains the benzene?
Yeah. Now, exactly how the benzene turns into the soot is not known. So there's the correlation that you see the benzene, and you look a little bit above it in the flame, and you see bushels of black stuff. Okay. That's known. How that magically goes from the benzene and acetylene, you can measure. You have a lot of benzene, a lot of acetylene, and then all of a sudden you got tons and tons of soot. And so that's a major research question right now. So one idea, of course, if you're trying to design a good device, is you don't want this to happen. So you just want to make sure you get the ethene and the propene into the flame near the oxygen quick before they have time to form the soot. And that's all about combustor design. And you're trying to make the combustor clean, has to do with making the flow field right so there's no stagnant area where it can just sit there and cook for a long time. Because if the fuel can cook under heat for a long time, it's going to be soot. But if you can somehow get it so that you can set up the shear rates correctly and the flows and everything right, so you can get it just right, so you can get it diffused into the flame quickly, then it'll all burn up and it'll be fine. Because primarily the mass is mostly the ethylene, so this is actually the most important thing, is if you can get the ethylene in there before it turns into acetylene, then everything will be fine. And you make a little bit of benzene, it's not such a big deal. Yeah?
So can you explain a little more about what's the difference between those two isomers?
With these two?
Yeah.
There are no difference. So they are just two ways to draw the same thing. And the real quantum mechanical thing is that there's actually one electron wave function going over the whole area, and this electron's just flying back and forth. Yeah. And unfortunately, we just use these Lewis structures, which can only draw the double bond in one place. But actually, this bond is unusually short for a CC single bond because it's actually partially double bond. It's sort of like a halfway. And the same with benzene, that all these bonds in benzene are actually the same length. They're not short, long, like you'd expect if it was double bond, single bond. Instead, they're all the same because the electrons are just tooling around there. In this case, you have 6 electrons tooling around, so it's really stable. Yeah?
How does ethylene turn into benzene? You explain this.
Nobody knows. I'll show you what people think about it. But I would say it's not completely known.
But the Glassman group is talking about C4 plus C2, right?
That's the hypothesis. There's numerous hypotheses. Sorry, replay the question. How does the ethylene turn into benzene? My answer is nobody knows. Another way to say it is a lot of people think they know. And they publish papers saying, here's the reaction, here's the other reaction, here's the third reaction. And I don't think anybody knows, is my opinion.
But this C3H3 is known.
A lot of reactions are known that make benzene. Which reaction is the one that's really dominant and important in a real flame is not known. If you just go into a lab and put one particular molecule in there, you can measure the rate. If you put a C4 and a C2, you can measure the rate coefficient, how fast it reacts, or you could do the calculation with the quantum chemistry. But in a real flame, the C4 and the C2 have a lot of other options of things that they can do. And whether they do this particular reaction that we're studying dominantly compared to other stuff, I don't know. And there's also other ways to make benzene, lots of other ways. And I think the current consensus is that as you change the flame, you can change which pathway to benzene is the most important one. And in a lot of flames, this one, the 2 C3s, this is actually, maybe half the benzene comes from this, and then the sum of all the other possible ways adds up. But if you start with, if you start with ethylene, you don't make any, you don't have hardly any, if you say pure ethylene to start with, it would be hard to make a C3, because all the carbons are already paired up. And in this case, it won't be. It'll be something like C4 plus C2 or something. It will be the way it's made. So the result sort of depends exactly what fuel you started with. If you still have fuels that are mixtures, you always have mixtures of ethylene and propylene. And then you usually have enough propylene that this pathway, which is very fast, is the dominant way. I was doing some fuels recently, make a lot of C5 pentagon rings. And then there's another pathway through C5. But I think that's just special to those fuels which make a lot of those rings. All right, so here we go. That's a great lead in. We really care about soot. We want to make sure we know how fast it's going to form because that tells us how we have to design our combustor. We basically have to make sure that all the fuel gets into our flame front before it's all turned into soot. That's our first objective at clean combustion. So you want the chemist to tell you, well, how long is it going to take before this stuff turns into soot? And I'm being a chemist, I have to admit, sorry, we screwed up, we don't know. So that's a really good question. And then also, you'd really like to know the particle size distribution of the soot. So the soot, different sizes will burn out with different times. And so you'd like them actually to be small for burnout. But then certain sizes are particularly bad for humans to breathe because they'll penetrate into your alveoli inside your lungs. And that would really ruin your day. So there's certain sizes you don't want to have. And then some sizes are like good for filtering out. So you really don't mind those sizes so much. So there's a complicated story about what size you want. But it would really be nice to be able to predict what you're going to get when you run your burner. And then you'd be able to figure out what you're trying to do. But unfortunately, we can sort of do that, but not really that well either. So this is like a very big research topic, is trying to figure out sort of the fundamentals, what's actually happening, And also, can we make quantitative predictive models that we could give to like the engine designers and combustor designers so that they could design their things to not make the soot at all, or to make the soot that's only of certain sizes that's not so bad or something. So let's take a little look at what Hai Wang said about this a while ago. Let's see if I can find it. So this is not the complete slides that he showed, but this is some of the slides he showed. So he got to give one of the plenary lectures at the 2010 Combustion Symposium in Beijing, which is kind of a big honor. So I think there's only like 4 plenary lectures or something in the whole symposium. And it was about this topic. This is a beautiful, sorry, yeah. Oh, it didn't go. How odd. Why didn't it do that? Huh. Is anybody here a computer person? Would know why? I'm seeing one thing here on my screen, and you're seeing something else. Sorry?
Minimize your first presentation.
Okay. No, I got that. Okay. This one I know how to get rid of. There we go. And you got it? All right. Okay, so this is a talk that Hai Wang gave. And I just wanted to acknowledge the people who organized this conference with a beautiful poster. That was a really fun conference. It was nice. All right, so this goes back to a fundamental question. Why do you get condensed phase matter sometimes? So we have all these gases, and all of a sudden we're making solids. What is that about? And there's 2 different things that can happen. You can have enthalpy driven. So you have reactions, say, with metals with oxides. It makes metal oxide molecules, but metal oxides themselves are just intrinsically solids. So you started with 2 gases, maybe metal vapor and oxygen, and when they react, they just make a solid. And it's just driven by the enthalpy. It's incredibly exothermic for that to happen. But you can also have entropy-driven things where you start from some molecule, say, with a lot of hydrogens, and if you can get rid of all these hydrogens, you end up with solid carbon. So this would be a process that would might be endothermic, but because you make a lot of moles of gas, the entropy will carry it. And so for soot, I think we don't know actually which one really wins, delta H or delta S. It's kind of close. So you can see here, if you start with some alkane, like this is propane, and you go across, it's kind of close for enthalpy. So I don't know if it's exothermic or endothermic. It looks like it's not that much different. Overall, free energy-wise, it's favorable. So delta G is negative, and that's primarily because of this first step, that when you go from, say, propane to acetylene, you liberate a lot of hydrogens. And so the entropy is driving that. Even though it's very endothermic, you definitely get it driven. If you're high enough temperature, so if you're above the ceiling temperature for that reaction, you'll definitely make this happen. The rest of the way, this is pretty flat, and maybe it eventually comes to graphite, I don't know. But these I don't know if it's uphill or downhill, and I'm not so sure. And so this is actually one issue with the soot chemistry models, is we don't know the thermochemistry of the large hydrocarbons that accurately. And it turns out that you need to know it pretty darn accurately to know on this flat surface, is everything going to flow down to the right, or is it going to flow back to the left? So that's one issue. But the first step, for sure, is entropy-driven. So at higher temperatures, you'll have the propane go to acetylene. At low temperatures, it wouldn't do it. Of course, you make it all the time. So it must, obviously, this whole process must be favorable, because it happens. And you've all seen the soot lots of times, and people have been using soot forever. This is back in the caves and from during the ice ages, 35,000 years before the present. This is an old cave guy from 3000 BC. He has tattoos made out of soot. So people knew about soot for a long time. And we've been breathing it a long time, too. And people have been studying it with microscopes for quite a while. And if you look at it with electron microscope, you can see these kind of onion ring structures or little flat things. And people think that those are little sheets of some polycyclic aromatic hydrocarbons, maybe 20, 30, 50, 100 carbon atoms in a plane. And then maybe they're bounded together with some CH2s or something, and nobody knows. But you can see it. And sometimes you can see some soot doesn't show this planar thing so much. So there's like amorphous soot and crystalline soot, and there's a whole way of people study about that. And it depends on the history. This is what's called mature soot. If you cook the soot for long enough, this is what you end up with. This is sort of the final state. But it doesn't mean that's the first state that happens inside the flame. You can, of course, use soot to help you. So there's some companies like Cabot make a fortune selling carbon black for tires and for Xerox machines and laser printers and ink and stuff. So that's all a great use of soot. And in combustion, we use it for heat transfer. So if you make a sooty flame, you can get the radiation to really carry a lot of the energy for you. So a lot of big furnaces work that way. So there's a lot of nice things to do with soot, as long as you don't breathe it. But unfortunately, we breathe a lot of it. So these are just photographs of the soot. There's actually a famous thing. Have you guys ever seen the line clouds? Anybody, raise your hand if you know what a line cloud is. Oh, you got it. Oh, one person. Okay. So this is something you guys have to look up. When you look up in Google, a line cloud. So over the Pacific Ocean, northern Pacific, there's these straight line clouds, just stripes, very thin, thousands of them. So they figured out what it was is that when the cargo ships travel between North America and Asia, they use really crappy fuel, and they have engines that don't have any emission controls. And so they put a lot of soot up in the air. And the soot nucleates clouds. And so you can see the route that the ship took, because there'll be a cloud exactly following the route. And so on the main shipping routes, there'll be like thousands of these clouds all next to each other, because all the ships went basically the same direction. And so you can see it. And it actually significantly affects like the albedo of the Earth, because they're like making these clouds from the soot. And then I think probably same thing downstream from, you have a old coal power plant that doesn't have emission controls. The same thing, the particulates coming out. And then you can see a line cloud just downstream of the thing, whichever way the wind blew. Yes, and the soot deposition is very important for the climate change. So the error bar in the climate change, a huge part of it, has to do directly with how much soot is being dumped on ice, on snow, because it's changing the albedo from white to black. So it really changes how much light gets reflected, how much gets absorbed. And then also, it nucleates the clouds. And if you make fluffy clouds, they reflect a lot of the light, so they change the albedo. So most of the error bars in the predictions of the climate change have to do with the clouds and the soot directly. So if you understood this a little bit better, you might be able to narrow down the error bars on the climate predictions. All right, so back in 1965, when I was a 2-year-old baby, these Palmer and Collis wrote a paper and said it would be a major breakthrough in understanding carbon formation if we could follow the course of nucleation and growth on carbon based on fundamental reaction rates and mechanisms. So I have to tell you the sad story is it's almost 50 years later, and we haven't quite got this yet. But we're still working on it. So they can recognize it's pretty important to do. And so there's some very important papers. Actually, Frank Luck and Wong had a very important paper in about 1990. And several other people. Bockhorn had several really important papers about this. There was a guy named Jack Howard, who used to be at MIT. He had a bunch of important studies of this. Sarafim also. And so there's a lot known about soot, but there's still a lot of mysteries about it. And now the soot models are getting good enough that people use them in the engine designs, like for gas turbine or aircraft turbine combustors. And they need to know, like, for example, what the heat load will be, so they need to know how much soot they're making. And you can use them, but the models have had some pre-parameters that were tweaked to make it work, and we don't really know where those numbers are coming from. It's just that people did experiments. They found that if you use these certain effective parameters for the soot nucleation and soot growth, at least if you stay within the range of kind of fuels they were using and the conditions they were at, you can predict pretty well what will happen. And it's good enough that it's used by the engineers. But it's kind of unsatisfying for the scientists because they don't really know what's going on. This guy, Kraft, he's been doing a lot of work recently in this, trying to bring the models up and connect them with all the experimental data. And then people like Howarth, and several groups actually that are doing turbulent flame modeling, putting in the soot, trying to figure out what's the interaction between the soot and the turbulence. Actually, Mike Mueller here at Princeton is one of the guys working on that kind of stuff. But just from the chemistry point of view, what's happened is that these first bits, through up to maybe here, maybe somewhere around here, this part is like really well understood now. And people have worked out all the rate coefficients, and we know the thermochemistry and everything. But then somehow you make molecules like this, and suddenly you see black stuff. And so this last part, it just goes somehow. And we haven't figured out exactly how that happens. And so this has different names. So I guess what we can say is that the regular gas-phase chemistry we understand pretty well. The pH chemistry for the smaller pHs we understand pretty well, but it starts to poop out as we get to heavier ones. And a big part of it is we don't even know the thermochemistry that well. And then this nucleation step, I'm going to talk about that, we don't really know it at all. And then there's the mass growth. We have an empirical parameter that works well to predict mass growth, but it basically says that all the soot, every time it bumps into a molecule, it just sucks up the molecule. So you have to make it like collision limited to explain it because it's so fast. But how that can be, why the molecules stick at such a high temperature, because you should be above the ceiling temperature, they should fall back apart. So why they stick is kind of a mystery. People have figured out recently why soot particles are almost always spherical when you look at them. It was kind of mysterious. So see they're round, but why they should be round? Because you start out making flat planes of like graphite or something. So how to get round? But that's understood now. And also the shapes of the particle size distributions was a big mystery for a long time, but recently people are able to predict that correctly. So here's a nice work by Marcus Kraft about the particle size distributions and then compared to the experiments. You see it's not quite right. We don't have the dip quite right, but you can see that we have here's the different particle diameters, what the probability of how many you form of them. And it's sort of at least definitely on the same page. And the same with the chemical makeup, how much pHs you have as measured with mass spectrometry, and here's what the model is. And again, it's not exactly the same, but you can see at least we're on the same page. So qualitatively, or semi-quantitatively, people are starting to get an idea of what's going on. And the experiments are getting better and better. For example, Hai Wang, who was the author of this presentation, invented a new flame geometry that has much better controlled boundary conditions. So you can do the simulations more accurately for the soot. And then these are, he would simultaneously measure the temperature, and he had a model, and the model really matches the temperature very well because he really understands its boundary conditions, which historically it's been a big problem, is that as soon as you make soot, you get a lot of radiation. And then you have to, if you want to calculate the temperature, the local temperature in your flame, all of a sudden it's different than what you would have expected because the radiation is taking the energy somewhere else. And then trying to calculate accurately what that is when you're not really sure exactly how much soot you have, and you're not really sure the radiation model that well, it's been a big problem. And then if you mispredict the temperature, then all the chemistry is mispredicted because we're in this regime where we're close to the ceiling temperature. So if your temperature is mispredicted, you might predict that it won't grow anymore when it really does grow, or vice versa. So it's been like a major headache for a long time. But people, you can see these are pretty fancy experiments and really understand it pretty well. And they invented new instruments, mobility sizers, for example, that are really nice for really measuring carefully what you got. All right, so we still have some problems with the pH chemistry. We have a lot of problems with the particle inception. How does the particles form in the first place? And then the composition, This is posed as a question, but I would say the answer is no, they're not the same. So the soot, when it's first formed, and the soot you measure coming out of a flame are different. And so that's the problem. Like, what the heck? So some reactions happened as the soot was traveling through the flame, and it changed the soot. But exactly what that was, nobody knows. Well, they know what the soot looked like before and after, but they don't know why or where the molecules went and what the atoms were doing. And then there was a famous mechanism called the Haka mechanism that for a while people thought was the answer to everything, and then I think they've now decided it's not, and really there's several different things happening. So quickly, well, maybe, let's take a break, and I'll come back and talk more about it.